Welcome to the last unit for college algebra. In Unit 5, we will study exponential and logarithmic functions. Exponential and logarithmic functions are a pair of inverse functions. That is, they execute exactly the opposite operation. In the same way that addition and subtraction are inverse functions, or multiplication and division are inverse functions, exponential functions and logarithmic functions are inverse functions. To really understand those two very important functions, we're going to lay a foundation here in section 5.1 for general inverse functions. This video will cover both section 5.1.1, Introduction to Inverse Functions, and 5.1.2, one-to-one functions. Introduction to Inverse Functions. An inverse function, f inverse, read f inverse of x, reverses the action of an original function. So we're going to consider two functions, and we will imagine their action using a mapping. So let's suppose that within this little cloud, every single point in that cloud represents a value in the domain of a function called f. F will apply some sort of operation to the input and pair it up with some value in the range. So this second cloud we will call the range of f. So again, the function f takes an input value, we'll call it a, from the domain, applies some sort of operation to that input, we name it f, and pairs it up with some sort of output, which we can call b. We could observe then that f of a equals b. Now, going from function notation to ordered pair notation, this means that the ordered pair ab is on the graph of the function which we're calling f of x. That's not new information. What is new information is an inverse function. So let's take a new function defined or labeled as f inverse of x, and we're going to use it to reverse the action of the original function f. So if f ends in the range, then f inverse begins in the range. So the range of f is the domain of f inverse, which means the domain of f is the range of f inverse. So I'm going to apply a new operation to b and map it right back to a. So observing from this mapping, we could say f inverse of b is a. So whatever operation the function f accomplished, the function f inverse is going to reverse or undo. Going from function notation to ordered pair notation, we could also make the observation that the ordered pair BA is on the graph of f inverse of x. For example, if our function is f of x equals x plus 5, then the inverse function would be x minus 5. We will see inverse operations paired together in inverse functions. Now, just as we see a reversal in these ordered pairs, a function and an inverse function are going to exhibit this reversal throughout all of their properties. This includes the entire switching of the domain and range, as we can see in our mapping function. Now, an inverse function only exists under a specific set of circumstances. So let's consider section 5.1.2, one-to-one functions. A function f does not have an inverse function unless it is a one-to-one function. Sometimes you'll see me abbreviate that 1-1. What this means, in a one-to-one function, no two x's can be the same and no two y's can be the same. If you'll remember back to the definition of a function, a relation is a function if every x has exactly one y. We are now making that restriction more stringent by saying every x can only have exactly one y, and every y has exactly one x. So there is a one-to-one correspondence between values from the domain and values from the range. To determine whether a function is one-to-one, we use the horizontal line test. That should remind you of the vertical line test. If you'll remember, we use the vertical line test to determine if a relation is a function. It tested to see if every x has exactly one y. The horizontal line test will work similarly but rotated 90 degrees. The horizontal line test will ensure that every y also has exactly one x. It works just like the vertical line test. It states no horizontal line can intersect the graph in more than one point. Example 1. Determine if the relation is a function using the vertical line test. So we'll have the opportunity to review that. If it is a function, state whether it is one-to-one using the horizontal line test. So example A shows the graph of the parabola. If you'll recall, we can attempt to construct vertical lines to intersect the graph in more than one point. On example A, there is no way to construct a single vertical line that intersects in more than one point. Therefore, we know that this is a function. So by the vertical line test, this is a function. Now, we're going to do the same thing, but rotated 90 degrees. So I'm going to attempt to construct a horizontal line to see if it can intersect in more than one point. And notice we have found a horizontal line that intersects in more than one point. This means it is not one-to-one. It is a function, but it is not one-to-one. So let me see if I can find a point that's a little clear here so I can label those ordered pairs. Notice right here, the ordered pair on the graph is 2, 6, and the ordered pair here is negative 2, 6. So notice we have one y with more than one x. So the x is not unique for 6. Therefore, it is not one-to-one. It is a function because it passes the vertical line test, but it is not a one-to-one function because it does not pass the horizontal line test. Let's look at the next example. The next example is a parabola on its side, and if we run the vertical line test, we quickly observe it is not a function. So by the vertical line test, this one is not a function. It is merely a relation. It does not satisfy the condition that every x has exactly one y. Since it is not a function, we don't have to discuss whether it is one-to-one or not. The last example would be another graph that passes the vertical line test. Every vertical line intersects in only one point, so this is a function. You should recognize that as a cubic function. Then we can also run the horizontal line test to see can we intersect in more than one point, and the answer is no. So by the horizontal line test, this one is a one-to-one function. That means every x has exactly one y, and every y has exactly one x. This would be an example of a cubic function, which means that my graph is increasing through that origin, and because it's always increasing, it does pass the horizontal line test. If it were more pronounced, like some of our cubics, then it would not pass the horizontal line test. So that's an example of a one-to-one function. It is important to know if a function is one-to-one, because if it is one-to-one, then it is invertible or reversible.